Guys, we need to work out what we're doing for a maths coursework. Anyone got any ideas? Anyone?
I have an idea.
George? George, what have you done? George, what have you done? George, where are we? Where are we? What have you done? What is going on? I don't understand. What the hell?
Ow! Danny, what have you done?
I have no idea. What's up, guys?
Oh, Gareth!
Oh my God, Gareth!
Oh, Gareth! Thor killed you. Oh, this must be a nightmare.
No, don't you see? This isn't a nightmare. This is brilliant. We can do all of our maths coursework right here, right now. Minecraft has everything. Everything we need.
That idea is genius.
Woo!
But first, background. We are going to be looking at number conversions and bases starting from decimal, then going on to binary, octal, and hexadecimal. Throughout this demo, this conversion table will be in the top right hand screen to help you follow through the examples. Decimal is the most common number system that we use and is in base 10. A base is a number of different symbols required to represent a given number, so in this case there are 10 different symbols that can be used to represent a decimal number. In this example we are given 12, so when 9 has been reached, the left number gets incremented by 1 and the cycle starts again. Binary has a base number 2, meaning that there are only two representable numbers, which are 0 and 1. The logic from decimal numbers is transferable to binary as shown in the table on the top right hand side of the screen. Octal has a base number of 8. This means that there are only 8 representable numbers which range from 0 to 7. In this example, 45 is in base 8, meaning it is an octal number. If you follow the pattern in the table in the top right hand side of the screen, you can see that 45 in base 8 is equivalent to 37 in base 10. Finally, hexadecimal is in base 16. With hex there are 16 representable symbols. These range from 0 to 9, then A to F. If you look at the conversion table on the top right hand side of the screen, you can see that 10 in decimal is equivalent to A. In this example, we are given 12C, base 16. Using the conversion table, we can see that C, base 16, is equivalent to 12 in base 10.
Now, back to Minecraft! Yay! To start with, we will be showing you how to easily convert an 8-bit binary sequence, base 2, to decimal, base 10. Each illuminated light represents a 1 in binary, and lights which are off represent a 0. The number which is shown here, for example, would therefore be 0, 0, 1, 0, 1, 0, 1, 1. Starting from the right, in decimal this means 1 plus 2 plus 8 plus 32, which equals 43. As you can see, binary numbers double each time from the previous number, making them easy to convert back to decimal. Now let's try a different example. This time the number would be 1, 1, 0, 0, 1, 0, 1, 0. So, in decimal, this number would be 2 plus 8 plus 64 plus 128, totaling 202. The doubling numbers are actually due to the fact that each one represents adding 1 to the power of the base number, which is 2 for binary. 2 to the power of 0 is 1, which is why it starts at 1, then 2 to the power of 1 is 2, 2 times 2 is 4, 2 times 2 times 2 is 8, and so on. This is helpful mostly when it gets to octal numbers, which is next. In octal, the first number is 8 to the power of 0, 1, then 8 to the power of 1, 8, then 8 to the power of 2, 64, and so on. However, as 0 to 7 can be represented in octal, each number is multiplied by the position number. So in this example, it will be 6 times 1, 2 times 8, 1 times 64, which equals 86 in decimal. This shows that octal numbers can easily be converted back into decimal. The same can be done for hex, as shown next. In hex, the range which can be represented goes up to F, so a sequence such as 1, 2C is perfectly fine. Again, like previously, the base number is multiplied by the position number, so it would be 16 times 0, which is 1, 16 times 1, which is 16, then 16 times 16, which is 256. So C times 1 would be 12 in decimal, since 12 equals C in hex. 2 times 16 is 32, and 1 times 256 is 256, meaning the total for 12C in decimal would be 300. This has been how to represent any decimal number in binary, octal, and hex. Using this information, we can now move on to adding and subtracting binary numbers. Adding and subtracting binary numbers shares the same logic with doing the same with decimal numbers. Let's take a look. So for instance, if we had the number 00010101 and we wanted to add this to 01011010, starting from right to left, adding 0 to 1 finishes with 1, which works both ways, so adding 1 to 0 also finishes with 1, but adding 1 to 1 ends with 0, in which the extra 1 is carried over to the left. This therefore means the finished addition on screen equals 01101111.
We have the two binary numbers 011011001 and 00110010. We will do 1 minus 0, which is 1. Now we have 0 minus 1, which you can't do, so we will go to the left and get a 1 from there and turn it into a 0. So now we carry the 1 into our original problem. If we go to the left, we can see that 0 minus 0 is 0, and then 1 minus 0 is 1. Now we have the same problem as before, 0 minus 1. Do the same again and carry the 1 and put it into the previous column. Now the rest are zeros, and the answer should be 0, 0, 1, 1, 1, 0, 1, 1.
Over to you, Beth.
Ow! Ow! Oh, fine. Fine, George. Fine. I'll go and do my decimal stuff now. Stupid George. Stupid thing. Decimals.
Sign and magnitude can be used to represent positive and negative binary numbers. The first bit is always the sign. The following bits are always the magnitude or value. For example, if we wanted to represent 14, this would be it. If we wanted minus 14, this would be it. If the first red lamp is active, therefore a 1, it is a negative number. The green lamps represent the value. If the lamp is on, it is a 1.
One's complement is another way to represent signed binary values. Negative values are the inverse of the ordinary binary value. Positive values remain the same. For example, 14 is represented the same as unsigned 14. Negative 14 is the inverse of 14. However, one's complement has an issue. 0 is represented twice by one's complement, once as a positive and once as a negative 0.
2's complement is a derivative of 1's complement. Positive values are the same as unsigned binary. Negative values are the inverse of unsigned binary, with a 1 added to the binary value using the addition George and Danny talked about earlier. This is how you represent 14 and minus 14 in 2's complement. The positive 14 remains the same throughout, while the negative 14 is the inverse of the positive 14 with a 1 added to the end. Another difference is that there is only one value of 0, all zeros, not 8 ones.
Fractions can be represented in binary in two different ways: fixed point notation and floating point notation.
Fixed point notation uses a fixed decimal point as its waypoint between the integer and the fractional part. This waypoint is known by the machine when it is being interpreted. Converting from a decimal fraction to binary is simple. You take the decimal fraction and split it into two parts. The integer part is converted to exactly as before, this time giving the answer of 13. The fractional part is handled in a very similar way, but instead of the exponent going up, it goes down instead. This time, the answer we get is 0.875. Now for an example of decimal to binary. In 14.5, we would convert the 14 to 1110. The 0.5 is converted in a similar way to the 14, except we're using negative integers for the exponent this time. 0.5 would go to 1000.
Floating point notation uses a similar idea to standard form.
Standard form is a way of writing down a number. Standard form contains four main parts: the significand, the exponent, the sign of the significand, and the number before the exponent, which is 10 in decimal. Standard form can be used to represent large numbers, small numbers, or any number in a way that is easy to read and easy to write down.
We're going to look at this 32-bit IEEE 754 format. This format is commonly used as it is the accepted standard in computing. This uses three different components to represent a number: sign of the significand, the exponent in BIOS 127 format, and the significand. The significand is represented as a binary value. Notice that the first value of this is a 1. It will always be a 1, since we are removing any zeros from the left until we get to a 1 value. This means that we never have to show this value in the format, because it will never not be there. The computer knows to add it in.
In binary, the sign is represented with a 1 or 0. The exponent is slightly harder. For this format, we use something called BIOS 127 format. BIOS 127 format gives us the best mix of precision and range of what we need. When a number is read by a machine, it adds 127 to the number to give it its correct value. Minus 27 would become 100, 63 would become 190. We then convert the new representation into binary in the regular way. In this case, giving 0, 1, 1, 1, 0, 1, 0, 1.
When we combine each of these parts, we get a number with a huge range and a high precision that can be easily stored by computers.
There were so many sheep.
Oh my god, the sheep went on forever.
Hey Gareth, do you remember that time when I killed you?
I do.
Oh, this was
Wait,
such
guys,
a good idea.
Guys! How are we ever going to get back home?
I have an idea about that.
Gareth, what's that sound?
No.
That's a terrible idea.